One disadvantage of the 5R covering theorem is that if the original collection of balls cover some set, then the subcover doesn't necessarily cover the original set. Only the balls of 5 times the radius do. But what if you want a subcollection that still covers a given set, but using the balls from the original collection, not their dilations? The Besicovitch covering theorem allows us to do this, but with the trade-off that the balls are, of course, no longer disjoint, but will have bounded overlap. Let's go over the statement of the theorem. So let B be a collection of closed balls in Rd, and let A denote the set of their centers. And we're going to assume that the set A is bounded. Then there are constants C and N, depending only on the dimension of the space and not on the collection of balls, such that the following holds. So first of all, we can find a subcollection, curly B prime, of bounded overlap that covers the set A. Right? And I've written this statement in a mathematical form here using these inequalities. So let me explain why these inequalities say that the balls in B prime cover A and have bounded overlap. So this first inequality says that the subcollection B prime covers the set A. Because notice that if x is in A, that implies the characteristic function A of x is equal to 1. But now, because that means that 1 is at most the sum of the characteristic functions of these balls, so that implies that there exists B in my subcollection such that the characteristic function of B of x is equal to 1. But that implies that x must be inside some ball inside my subcollection. And that's what it means for the set A to be covered by the subcollection B prime. Now, the second inequality says that my subcollection has bounded overlap. Okay, so the reason why is suppose that I had a point x that was in C plus 1 many balls. Well, then that would mean that the characteristic function of x here would be equal to 1 for at least C plus 1 many balls. But that would mean that this sum here would be at least C plus 1 and hence exceed C, which is a contradiction. And thus, if the characteristic functions satisfy this inequality, that's equivalent to saying that the balls have bounded overlap. No point is contained in any more than C many balls from the collection. The second part of the theorem says that with this subcollection of bounded overlap, we can in fact split this collection into further subcollections, curly B1 all the way up to Bn, where each collection is a collection of disjoint balls. So let's take a look at an example. So on the left, I've generated a random collection of balls in the unit square. So the blue dots denote the centers of these balls, and the gray circles denote the boundaries of these balls. So you notice on the right, I have a subcollection of this original collection that contain all the centers of the original collection. So you notice that all the blue dots are contained in some circle. And moreover, if you pay close enough attention, you'll see that any point in the unit square is contained in no more than 4 many balls. Furthermore, this subcollection, as you can see, has been divided into 4 different subcollections, each with its own color. So you see there's a green collection, there's a red collection, there's a violet collection, there's a yellow collection. And for each of these collections, you'll notice that the balls are disjoint from each other. So none of the green balls touch each other, none of the violet balls touch each other, none of the red balls touch each other, and none of the yellow balls touch each other. So this here is an example of a Besicovitch subcovering of the collection on the left. So as an example to show how the Besicovitch covering theorem is used in practice, we'll prove yet another version of the Hardy-Littlewood maximal inequality. Now this one only holds in Euclidean space. However, it has the advantage that it holds not just for Lebesgue measure or doubling measures, it holds for any Radon measure in Euclidean space. So again, recall that the Hardy-Littlewood maximal operator defined for a measure mu is defined as usual Hardy-Littlewood maximal operator, but now we take averages with respect to the measure mu. So again, I'm going to call this set here E sub lambda, and my goal is to bound the mu measure of this set. Okay, so again, without loss of generality, I'm going to assume that my function f is non-negative. Now, in order to apply the Besicovitch covering lemma, I need the centers of my balls to be in a bounded set. However, the set E lambda may not be bounded. But what I do is I say, I'm going to define a set E lambda R to be equal to E lambda intersected with a ball center at 0 of radius R. And now, because the limit of this set as R goes to infinity is equal to E lambda, that implies that the measure of E lambda R converges to the measure of E lambda as R goes to infinity. And so this implies that there exists some positive number R such that the measure of E lambda R is at least 1/2 the measure of E lambda. So thus, if I can bound the measure of E lambda R from above, I can bound the measure of E lambda from above. Okay, so for all x in E lambda R, by virtue of being in E lambda R, I know that there exists some ball Bx centered at x such that the average of f with respect to mu over that ball is bigger than lambda. So I'm going to define my collection of balls to be the set of Bx such that x is in E lambda R. And we can see that the centers of the balls in this collection are exactly the set E lambda R. Okay, so Besicovitch now implies that there exists a subcollection of bounded overlap. And such that the centers of these balls, i.e. the set E lambda R, is still covered by this collection. So now, mu E lambda, so recall that this is at most twice the measure of E lambda R. Okay, so this is at most mu of the union over the balls in the collection B prime. By subadditivity, this is at most the sum of the measures of B as B ranges over the balls in my subcollection. Now, recall that by the balls in my collection satisfy this inequality. Okay, so notice that if I multiply both sides of this inequality by the measure of Bx, or the measure of the ball, and divide both sides by lambda, it gives me that mu of the ball is at most lambda to the minus 1 times the integral of f over that ball. With respect to mu. Okay, rewriting this slightly differently, this is the same thing as the sum over B and curly B prime of lambda inverse of the f times the characteristic function of this ball. Okay, now by Fubini exchanging, or Tonelli rather, using interchanging the sum and the integral, this is equal to the integral, I'll pull the lambda minus 1 outside as well, of the sum over B and curly B prime of, I'll put the f out here, times the characteristic function of these balls. Now, by the bounded overlap property, this is at most, this sum of characteristic functions is at most some constant c. So this is exactly c over lambda times the L1 norm of f with respect to the mu measure. And that finishes the proof of this Hardy-Lillard maximal inequality. So next up, we'll show yet another application of Besicovitch covering lemma, improving yet another covering lemma, the Vitali covering theorem.